There we are. There we are.
There you go. Yes.
Okay, so let's start so we keep things on time. It's a pleasure to have Ricardo Stuardo. That's the title of his talk. And Ricardo, go for it.
Well, thank you very much, Carlos, for this wonderful introduction. And thanks again to the organizer for putting together such a wonderful event. I'm going to talk about this work that we did a couple of months ago with my supervisor in Swansea University, Adi Armoni. Well, there is the archive number. And it's about dualities of three-dimensional n=1 supersymmetric QCD theories from Branes and there's non-supersymmetric deformations. I'm going to mostly talk about the duality, and I'm not going to focus so much about the non-SUSY deformations because it would take a lot of time. So I apologize for that. So the outline of the talk is the following. I'm going to start with a very brief motivation on why I am going to show you what I do. Then I'm going to spend most of the talk talking about brain dynamics from like a very basic perspective. I was asked to be like generous with the introduction, and I think this should be enough. And then I'm going to talk about the main result, which is the dualities of three-dimensional n=1 theories. Then in the end, I'm going to talk about non-supersymmetric dualities, which I think is one of the most important points in my work with Adi. And then I'm going to finish by giving a summary and outlook of the talk. So it should ring something in everyone's head when I say that the strong coupling regime of non-abelian gauge theories is not perturbative. This is something that probably you've heard some other people talking in the back of the room, or it's a very well-known problem. And there has been a lot of progress understanding the strong coupling regime of a cousin of gauge theories which have different degrees of supersymmetry. And one of the key ingredients to understand the strong coupling dynamics was the strong-weak dualities. And one way to obtain these dualities is to embed the gauge theory in string theory. And the gauge theories are embedded as the low-energy effective theory on the branes. I'm going to say, sorry, what a brane is in a minute. But to say that the brain dynamics will allow us to give a geometric description of different gauge theory phenomena. So we will see, for example, that flavor symmetry breaking patterns, which could be hard to derive from the field theory, are just appeared geometrically in the brain system. So I will be focusing mostly on a wonderful review about brain dynamics of Givion and Kutasov. Not Kutason, sorry. So in string theory, the p-branes are objects in which open strings can end, and they preserve 16 out of the 32 supercharges that one can have. The massless bosonic excitations of an open string ending on a brane are split into two. So the ones that are parallel to the brane, so if my hand is the brane, the ones that are parallel, they correspond to a gauge field, and excitations which can be transverse to the brane, which represents fluctuations of them, are scalars. And we will have, the number of them will depend on the number of scalars depend on the dimension of the brane. But if we only, in string theory, there are more than just massless modes. So we'll have massive modes on the brane and also closed strings, massless or massive, in the bulk. And if we only want to study the theory of the massless modes, we need to decouple them from the rest of the excitations. And this can be done consistently by taking what is called the decoupling limit, in which we send alpha prime to 0 by keeping the effective Young-Mills coupling fixed. So this is by tuning G strings and alpha prime in such a way that the Young-Mills coupling is fixed. Having done this, what we have after decoupling everything? We have a theory in a p+1 dimensional space-time. The theory preserves 16 supercharges, and it contains a vectors and some sets of scalars. And from this data, the only option that we can have is Maxwell's theory, but it's maximally supersymmetric version. Okay, and probably if you've taken a string theory course, you know that if you stack branes on top of each other, you get not U1 theory, but actually a SUNC theory. So this construction will give you the maximally supersymmetric Young-Mills in p+1 dimension. So we have the Young-Mills term, the kinetic term for the scalars are their potential, and obviously we have fermions, but for the rest of the talk, please let me write plus fermions to say that there is a supersymmetric completion. But it seems that if I have a brane, I can only get a theory that preserves 16 supercharges. And this opens two questions. First of all, in maximally supersymmetric theories, there is only one multiplet, which is the vector multiplet. So I only have matter that transforms in the adjoint representation of the gauge group. So one question is, how can we add matter that transforms in a different representation, for example, the fundamental representation? And another question is, can I realize theories that have less supersymmetry? Well, the answers to both questions is yes. And for this, we need to consider branes ending on branes. So we will have, I'm going to show a drawing in what follows, but we'll have branes ending on a special type of branes called NS5 branes, which basically act as a wall in which they can terminate. These setups in general will also allow us to introduce fundamental matter. In particular, we'll be interested in realizing three-dimensional gauge theories with some amount of supersymmetry. And the brane setup that has an effective theory, it consists of a stack of D3 branes suspended between two NS5 branes at a distance L. So this is the picture that I want you to have in mind. Please note that the D3 branes and the NS5s share the X0, X1, and X2 directions, which we can think of them as the field theory directions because we want a three-dimensional theory. The NS5 brane, being a 5 brane, has another 3 extra coordinates, which are X3, X4, and X5. And note that the D3 brane is point-like in those coordinates, and the D3 brane will have it extended along this X6 direction. So the picture depicts everything that is not the field theory directions. So these walls are actually a three-dimensional space-time, and the branes are point-like in this space. So as I said before, the fluctuations of the brane are realize the scalars of the theory. We will, by construction, we will always have the vector field. So let's look at the scalars. So we can think of the NS5 branes as a wall. So excitation which are transfers to this wall, they get suppressed by a mass which is 1 over L. And excitation which are parallel to the brane, so if the D3 moves like this, are massless. And because there are 3 directions, we will have 3 scalars. And so something that you can ask is, oh, but Ricardo, the 3 branes are actually realized 4-dimensional theories. That's true, but because we have them extended at a finite distance, at scales which are lower than 1 over this distance, the theory is effectively 2 + 1. This is exactly the same as Kaluza-Klein theory, where if you are below the Kaluza-Klein scale, you don't see all the massive modes, and the theory is effectively 1-dimensionless. This is exactly the same. If there is any question here, there should be asked at this point, because this is like the building block of whatever I'm going to do next. Well, if not, I'm going to continue. So now instead of drawing this as planes, let me just draw them as straight lines. So let me say that the previous configuration preserves 8, so half of the 16 supercharges, but only realizes the vector multiplet. And we can add fundamental matter in the UNC representation by adding NF semi-infinity 3 branes to the left of this is a convention of the leftmost NS5. So in this way, so we'll have 3 types of strings. The blue ones, which start and end on the D3, will realize the vector and the scalars, so the fundamental matter, the adjoint matter. The green one, which starts in the flavor branes and ends on the color branes, one can think of them as we have one flavor index and one gauge index. So they actually correspond to matter, which transforms in the fundamental representation and also has some global flavor symmetry. But there also seems to be a gauge theory for UNF, because we have this string that starts and ends on the flavor branes. But this is not the case, because if one looks at the effective Young-Mills coupling, it goes like the 3-dimensional one goes like the length of this brane times the 4-dimensional gauge coupling. And because this brane is semi-infinite, this goes to infinity, and effectively the gauge degrees of freedom on the flavor brane are frozen. So from the point of view of a 2 + 1 dimensional observer, those degrees of freedoms are frozen. So in the end, the effective theory preserves 8 supercharges, and the bosonic content is UNC gauge theory with F fundamental bosons, or let's call them flavors. Okay, so this is 8 supercharges. We can further break it to 4 by, if we have the wall like this, now we can rotate one of them, and know that now the directions in which the D3 brane can fluctuate, which is parallel to both of the NS5s, is now only the X3 directions because they are extended in different ones. This rotation locks 2 out of the 3 directions in which the brane could move. So now the vector multiplet has only one scalar, but it's what we expect from a theory with 4 supercharges in 3 dimensions. So this theory realizes, again, n equals 2, UNC gauge theory with NF flavors. But in 3 dimensions, when one has gauge theories, one can also introduce the Chern-Simons term. And there is also a way of introducing this in the brane configuration by using 1, k branes. Please let me not be so precise about this and just say that these are a combination of an NS5 brane and a k D5 branes, which are oriented in this way. But the point is that in the X3, X7 plane, this recombination looks like a brane which is tilted in that plane. But please let me not say more about this because it will take a bunch of time. So the final setup looks like this. We have the color branes, the flavor branes, and the tilted phi brane. And we can see from the spectrum but just by looking at strings, the field content of this theory. So the blue strings will give rise to the n equal 2 vector multiplet. The red strings will realize the flavors, and the green string realizes the Chern-Simons term. So this is the picture that I want you to have in mind. And this is the brane configuration for n equals 2 SQCD. And this will be the starting point of what I want to say. So the last ingredient is what happens when we move a D5 brane across an NS5. And this was presented in a really good work by Hanani and Witten in 1996. And basically, they show that as you move the D5 brane across, there is a D3 brane created which connects both of them. So it's the picture that I have here. Having said that, we can finally derive the n equals 2 duality. This is important, the n equals 2. So basically, what we're going to do, we have the NS5 brane, we have the tilted phi brane, and we're going to just move them across each other. When this happens, because this tilted phi brane has some D5 brane charge, there are some D3 branes created, as I showed in the previous picture. So now in the the starting point is the figure on the left. Let me call it electric theory. The final point is the theory on the right. Let me call it magnetic theory. And you see that in the magnetic theory, the number of color branes is different, and it's given by this combination of the Chern-Simons level, the number of flavors, and the number of colors. And this just by doing this brane transition, we have derived a field theory duality between a UNC theory and a UNC tilde theory. Any questions so far?
Ricardo, it's not a question, it's 5 minutes left. Okay, 6 minutes left. Okay.
Yeah, sure, perfect. So in order to derive the n equal 1 multiplet, the n equal 1 dualities, we need to break supersymmetry further. And this is done by noting that the n equals 2 vector multiplet can be split into 2 n equal 1 multiplets. The same happens for the n equal 2 scalar. And so we can integrate them out by giving masses to those fields that we don't want. And in the end, we integrate out those fermions. And by doing this, the Chern-Simons level is shifted in this way. So this is the n equal 1 theory that we obtain after integrating out those fields. So then after doing the same thing, both sides, we cross the branes and we get this duality here, which was obtained before, only using field theory language by Choi, Rochek, and Sharon. And let me go a little bit faster. We can check that this duality works by matching the Witten index on the electric and magnetic side. On the brane configuration, this is just done by counting different supersymmetric vacua. which basically means we reconnect branes and we count in how many ways we can reconnect them. And this precisely for the magnetic theory gives this number here. You do the exact same computation for the electric theory, gives the same number, the index match, the duality works. We can also, it seems to be the same slide, but it's not. We can also derive the flavor symmetry breaking pattern of the electric theory by looking at the magnetic theory. So from the same picture, we can see that the UNF symmetry is broken at one of the vacuous to UNF minus N times UN. And there is also a Wess-Zumino term, which kind of is like a Chern-Simons term, because this the 5 branes end, or the 3 branes, sorry, end on this, on the tilted 5 brane. And from the when supersymmetry is completely broken, the color group is completely Higgs. So the flavor symmetry breaking looks like this. And with the Wess-Zumino term is the one that you can see here. The level is precisely NC. And this same symmetry breaking pattern with the same Wess-Zumino term was derived on the electric side by Komargowski and Seibert, but only using field theory computations. So from the magnetic side of our duality, we've derived something of the electric theory. The last thing that I want to say is that we also looked some non-supersymmetric dualities. So we consider NC tilde less than 0. So you can ask me, Ricardo, what does it mean to have a gauge theory which has negative rank? And the point is that it's just an artifact of the branes. It's actually not that the rank is negative, but the point is that we have anti-branes. So Adi, in his solo paper, he studied the case with no flavors, and he derived some, he recovered the phase diagram of SUNC theory by looking at its non-supersymmetric brane configurations. And in our paper, we generalized his result to have the presence of flavor. We show that also the phase space is divided in 3 parts, but now the theories, each part depends on the number of flavors. One open question that we had is that you can say, oh, Ricardo, but you consider UNC theories, but now you're talking about SUNC. So the point is that we believe that in the non-supersymmetric case, there's something that happened that we cannot see from the branes, but the U1 part of the UNC should decouple, and that's how you end up with the SUNC. So let me summarize to finish. We studied 3-dimensional n=1 duality from branes. We showed that the duality works by matching the Witten index. We showed how the flavor symmetry breaking patterns appear in the electric theory, but by looking at the magnetic theory, something that I didn't show, but we actually did in the paper, is to study non-supersymmetric deformations and show that the deformed theories are still dual through level rank duality. We also derived some non-supersymmetric dualities and their phase diagram, and something that we also did, but I didn't show, is repeat all of the previous things, but for SO and USP groups. So, and in the future, we would like to do exactly the same thing, but in 4 dimensions. That is to study Seibert duality in the case in which the flavors are less than the colors. The aim of this is that on the electric side of that duality, there is a superpotential that appears perturbatively, non-perturbatively, and we hope to see that in a perturbative way from the magnetic side. And we also would like to study by lifting the configuration to M theory to analyze the Seibert-Witten curve of this non-supersymmetric configuration. And that's everything. Thanks. I hope I made it in time.
Thanks very much, Ricardo. Very, very nice, very clear talk. Questions, people?